So we're moving into a new chapter, chapter 3. It deals with one-dimensional steady-state conduction. It really takes chapter 2 and the math and the differential equations and builds on it. We'll go back to the differential equation and solve some more for the temperature distribution through a particular medium, through the slab, through the wall of a cylinder. It's a long chapter. I truncated it here. We're going to get to the thermal resistance concept. And then we'll get to contact resistance. I don't make a big deal of porous media. If you need to study porous media, it's pretty intuitive what's happening. You need effective thermal conductivity. And then we'll make, I think I skipped this one totally. We just don't have time for alternative conduction analysis. It's straightforward, but I just skip it. And then later we'll get to it. I don't think we'll get to it today, but radial systems. The heat transfer through a wall of a cylinder or the wall of a sphere. Okay, let's press forward. So, as the chapter titles describes, we're going to be solving the heat diffusion equation, one-dimensional, steady-state heat transfer with no heat generation. So what does our general heat equation look like in the rectangular coordinate system? Well, temperature is a function of x, y, and z, so that's the Laplacian. Those are the three components of the Laplacian of the temperature field. And then you have q dot, but you said, hey, q dot's equal to 0 when there's no heat generation, so that term goes away. Oh, you also said it was one-dimensional, so let's just do 1D in the x. And then if it's steady state, what about that term? So the whole equation boils down to, I love that one, don't you? Easy. That's the easiest partial differential equation that you'll find. And then we give two appropriate conditions, in this case, two boundary conditions, and then you solve it. All right. Well, for the cylindrical, I think it's useful to do the same thing. What does my big, long equation look like? For our heat diffusion equation, if you had the transient term, if you had the heat generation term, if you had temperature as a function of z and theta and r, and then say, no, we're going to be interested in one-dimensional only in the radial, no heat generation, steady state, and voila, the next easiest, PDE. This one's the easiest, and this one's close to it. And, hey, Professor, what happened to this 1 over r out here? Did you drop it? It seems like it got lost. What happened to it? Can you tell? You just multiplied both sides of the equation by r, and we got that the right-hand side was 0, so that's what happened to it. It's not a typo, it's just a simplification. All right, and then in the spherical. Now, I didn't have enough room to write out the whole expanded, or I didn't want to, Laplacian in the spherical coordinate system because I knew I would just throw away everything but the radial component. And then likewise, no heat generation, transient. So you get this equation. Again, somebody may say, hey, what happened to the 1 over r squared? Multiply both sides by r squared, and it goes away. So there you go. There's my simple. So these are really kind of easy equations to solve. I mean, you spent the whole class in studying differential equations, and these are the easiest. Let's just focus on the wall. I don't think we'll get to the cylinder and sphere today. We'll spend a lot of time just on the wall. So we have a wall of thickness L. We've been analyzing this type of problem before. It has this area over here that the heat is going to be flowing through, that perpendicular cross-sectional area. And it has a thermal conductivity of the material, K, and it has specified temperature. Let's introduce a coordinate system. The coordinate system is X running from 0 to L. So the wall has thickness L. Okay, and then it has at the temperature at x equal to 0, we'll call T1, and the temperature at x equal to the L is equal to T2. So the temperatures are specified at the faces. Okay, somebody says, I want you to solve for the temperature distribution as if you're the first person ever to do it. Set up that governing partial differential equation, turn it into an ordinary differential equation, two initial conditions, separate, integrate twice, and lo and behold, not to insult you, but there it is. You want me to do it or not?
Please.
Okay, well, here's our governing differential equation. Second derivative of temperature with respect to space is equal to 0. Was that not our governing differential equation? And here's my two boundary conditions. So I'm going to call this boundary condition number 1 and boundary condition number 2. Now we can start. So if you do the first, I'm going to call this the separate step. Separate. So it becomes the derivative of the first derivative of the temperature with respect to x equal to, or the change, dx, but that dx is times 0, isn't it? So doesn't that whole right-hand side go to 0 when I separate? It's kind of a silly separate, but there it is. What's the next step after separate? Integrate. So it's like I introduced the integration, but over here I have nothing. So all I'm going to pick up is dt dx is equal to a constant. Okay, I'm halfway through. I'm going to leave that as a constant C1. My boundary conditions, there's nothing given in the terms of a derivative at either 0 or L or R naught or anything. If there was, a lot of times I can use one of the boundary conditions and get rid of that constant right away. All right, now, so we had the separate step, we had the integrate step. What's the next step? Separate again. So we get dt is equal to C1 times dx, and then we just integrate. That's our integration step. That constant can come outside the integral. So we do the integration step, and you have t is equal to C1x plus C2, two constants of integration. Okay, now I need to apply the boundary conditions, so I'll have t at 0 is equal to t1. I'm just restating this first boundary condition, and that t1 is equal to c1 times x is 0 plus c2. So I find that c2, the second constant. Okay, computer. C2 is equal to T1. That's what I conclude. Okay, let's now go to the second boundary condition. So T at L is equal to T2. That's equal to C1 times L plus C2. I can write C2 there, or I can just go ahead and put what I know C1 to be, which is T1. So I take a look at this equation, and I say I can solve for the constant C1. C1 is equal to T2 minus T1 divided by L. Now we can re-express the solution. It's kind of like I just was able to solve for C2 and C1, so let's rewrite the solution. So T as a function of x is equal to C1, which is T2 minus T1 divided by L, times x. See how I just picked up this, just did it for that term? And then we have plus C2, which was T1. I pause. This was what we said it was going to be. And we compare our work. And does it look okay? Thumbs up. Very good, thank you. So now that we solved for the steady state temperature profile through it, and if you wanted to, we plot temperature, making use of this y-axis, and maybe up here is the magnitude of T1, and maybe over on this side the magnitude of T2, and it's a straight line temperature profile. Steady state through a slab, it's a straight line temperature profile. Okay, and it has a constant slope. The constant slope is negative because it's going from hot to cold. I'm showing it T1 is higher than T2. Okay, somebody says, can you calculate Q through the wall? Well, you're going to have to tell me how large of an area that is for this wall. Don't forget that. And you're going to have to give me the thermal conductivity of the wall. And then using Fourier's law, we know that dt dx. Now, we just talked about it. dt dx is at 0 is equal to what it is at L, what is it equal to at any place in there. The slope is not changing. The slope is the same no matter where you are in the wall. It's a steady state slope. So I can put this at 0, I can put this at L, I can evaluate that derivative anywhere. Okay, but let's go and evaluate that derivative. So we just solved for it. So what is dt dx from our... Isn't that easy? Isn't that just going to be T2 minus T1 divided by L? And I just noticed my mistake that I left out. What did I say I would leave out? Do it all the time. Oh, that's terrible. I shouldn't teach if I can't get the equation right, should I? No, what did I leave out? I left out that negative sign on that Fourier's law because that's going to be needed. So now when we substitute in for Q, Q is equal to, I'm going to take that negative sign and switch the T2 minus T1, and then I'm going to put the K, the A, the L, and I'm going to put the T1 minus T2. Why did I want to put T1 minus T2? Because I don't like negative entities. I have too many negatives floating around as an engineer. I like to work with positive things. And T1 is high and T2 is low, so delta T is positive. And so this is my equation for the rate of heat transfer. K times A divided by L, all of that, times T1 minus T2. The temperature difference driving it through the slab. Now, what we're going to do is we're going to introduce the concept of thermal resistance associated with that wall, and the equation is L over Ka. Where did that L over Ka come from? This grouping of terms right there. So let's do this. We come over here and we say, do you remember anything about electricity and physics 2 and EE 2213, that whole course in circuits, right? And the simplest part of the circuit is just a resistor. And so you have a little resistor like this, and you have something flowing through the resistor. You call that I for current measured in amps. And you had R as the resistance of that resistor in ohms. Maybe I should put like ohms. And this is measured in amps. True? But what drives the flow through the resistor? Something, and I'm going to put E here, even though you probably used V, E. Why? Because E is the electromotive force. That's an old term, but it's measured in volts. Otherwise, it's volts in units of volts, and that becomes confusing. Okay, V in terms of V, but that's the way I learned it. I learned volts in units of volts, but I kind of like to say it's electromotive force, E, in units of volts, just like I say it's resistance in units of ohms and current, I, in units of amps. Okay, so Ohm's law. You know it? Sure, E equals IR, right? Something like that, but it's really not. If this was 5 volts over here and 5 volts over there, would there be any flow through it? No, but if there was 5 volts and 0 volts, yeah, there would be a potential difference. So in Ohm's law, we remember something like E is equal to IR, but really I would like to re-express it as I is the flow, and you had the difference in the electromotive force, the voltage difference across that resistor. That's what drives the flow, E2 minus E1 or E1 minus E2 divided by R. And probably I don't like my subscripting here. I probably just want to put E1 and E2, call this E1 here and E2 there, and then it's consistent. It's flowing through that resistor. So we read our equations. We say we have some flow is equal to something that drives it, some potential difference that drives it divided by some resistance. That's what this equation shows us. It's I is equal to delta E divided by R. I know that it's E equals IR is a little easier to roll off the tongue, but we want to write it that way because that's the way we really wrote now the thermal flow. And we have an analogy between the flow of electricity and the flow of heat. There's a strong analogy. Okay, so the analogy is basically on the equation we just derived, which was from Fourier's law to get the Q, the rate of heat transfer through that slab. Now, this was our equation. We had that the rate of heat transfer through the slab was the temperature difference. I'd like now put T1 minus T2. It's consistent with my other slide, but you see I switched them. And then I divide by some resistance. That's a thermal resistance. Maybe I add a subscript T to say thermal instead of electrical. Maybe I leave it off because, hey, this whole book is about thermal, heat transfer. And I look at my equation and I just do a little name calling. The name calling is that is equal to L over Ka. I know you have to flip it, but I think you can do the flipping. And now we see that, we have our flow, just like our current. We have something that drives the flow. The difference in temperature drives the flow. If one side of the slab is 20 degrees C and the other side's 20 degrees C, they're the same temperature, steady state, nothing's happening. But temperature difference drives the flow, and then we have electrical resistance. The analogy is thermal resistance. And that thermal resistance, the biggest equation, probably in this class, other than the heat diffusion equation, Fourier's law, is just L over Ka. That's the resistance. Steady state flow through a layer of material. L over Ka. Hey, what was L again? Length. What was K again? Thermal conductivity. What is A again? Our area that's perpendicular to the flow. Now you say we have a slab, maybe here it's a T1 high, T2 low over here, but then it's exposed to a fluid, and the fluid has a temperature kind of down here, T infinity. And somebody says steady state heat transfer, the profile is going to be something like that, but when it gets into the fluid, it looks something like that. That's a not so good looking profile, but like that. Okay? There's typically a sharper transition in temperature in the fluid adjacent to the solid. Okay, but we already had a way of describing the flow of heat. We said, this is going to be conduction, this is going to be convection, this is Fourier's law, this is Newton's law of cooling, cooling law. And we boiled this one just down. We just said, look, this is the flow of heat through this steady state again. It's the same as that. So what is moving through the slab in conduction is equal to what's going out in convection. And our equation for the conduction was Q is equal to the T1 minus T2, what drives the flow through our slab, steady state, no heat generation, divided by our resistance of the slab, L over Ka. Resistance is L over Ka. I'm trying to summarize it. But now we say, what was our equation over here? Well, Newton's law of cooling. Q is equal to HA, the temperature at the wall, Ts, which is now T2, minus T infinity far away. And so you say, can I have a similar resistance? Same kind of concept? Sure. It's Ts minus T infinity divided by 1 over HA. So you do a little name calling. The resistance for convection is 1 over HA, just like the resistance for conduction through a slab is L over Ka. 1 over HA, L over Ka. You see that. So this is our convective resistance. Yes, we can get a radiative resistance, but because it's got that T to the fourth and it's approximation, let's skip it for now. Let's just worry about conduction and a boundary condition, convection. We'll get more complicated as the semester goes. Oh, clicker time, huh? So, the convective thermal resistance equation, we just got it. 1 over HA, true? What are the typical SI units for that? So would they be watts per meter squared, or meter squared per watt, or meter squared degree C per watt, etc., degree C per watt, or watt per degree C? So what are our typical units for that? I'll give you a little time. I'd really like you not to look it up, but to work it out on a piece of paper. You know, you should be able to work out those units. There, 1.5 minutes, okay? Is that enough time? All right, we're down to the last 15 seconds. So let's go ahead and take a look at the results. Hey, that's pretty good. That's right. And so those that are know that they can change their answer now, quickly do. And those that don't realize that next time, one person, next time you're going to really jump on it. It is degrees C per watt, right? Good. Work those things out. Test yourself as you study and check your units. A lot of times it'll help you avoid an error. Okay. All right, so a lot of times we have a wall made up of not just one material, but multiple materials, such that you have a layer of this material, maybe a layer of that material, and a layer of another material. Call this material A, material B, material C. This is very, very common. If you're going to take the FE exam, the Fundamentals of Engineering exam, at the end of your career, your last semester here, I strongly encourage you to do it. You need to do it to begin your process to become a PE. And you want to become a PE. Believe me, you want to become a PE. All right? The world is getting more and more litigious, more and more certificate-driven, education, credential-driven, etc. And maybe at the start of your career it won't be important, but you're going to need it. That's just the way the world's changing, okay? You need to pass this exam. I'm going to tell you, this material right today is on that exam. Guarantee the heat transfer section. Easy. This is easy. So you have a material and you have the thickness of slab A, the thickness of slab B, the thickness of slab C. Notice I tried to not show them all to be the same thickness. And so you have the thermal conductivity of A, the thermal conductivity of B, the thermal conductivity of C. And you have the flow of heat through this material. So if it's steady state, you have to check that and make sure it applies. But often we're interested in rates of heat transfer at steady state. And there's no heat generation. Got to check that, but that often applies. And you have some temperature way over here. Let's call this T1. You have some temperature at that interface, T2. There's some temperature over here at this interface, T3, and some temperature at this interface, T4. You want to add fluids? Fine, call T0 and call T5 out here. Those are our fluid temperatures. And you could have the flow of heat through a network. And it's the easiest network. It's a series network of resistors. So maybe you would start, you put a node for where you have your temperatures. And in between the temperature nodes, you have little thermal resistors. Here I'm trying to line up the location of the nodes with the spatial location of the temperature at the interfaces. Okay, but this would be the node temperature T0 to temperature T1, the value of the temperature T2 at that node, T3, T4, and T5. Notice, in our equivalent thermal network, temperatures are at the nodes. And then what we have is we have the flow of heat Q through it. And so if I have 5 watts through that first resistor, it's 5 watts through the second, all the way through, and 5 watts getting dumped out at T5. And then we have our resistance. Now this is a convection resistance. That's a 1 over HA. And that H is on this side. Let's call it, I don't know, let's call this the outside. And so that'd be H on the outside. Over here I have 1 over HA. It's a convective resistance. Maybe this is convection on the inside. So I'll put a HI for subscript I for inside. And then we have 3 L over KAs, L over KA, and L over KA. Those are 3 slab resistances. And we just have to say, okay, the first slab is length of material A and thermal conductivity of A. A little cumbersome because I have A for area and then I have A for that material. But so you just have to pay attention. And then this is B, B, and this is C, C. So you have to use the thicknesses and conductivities of all those components. You ready to solve a problem? That looks simple enough? And so how do I get an equivalent resistor for that network of resistors in series? When in series, add them up. Exactly it. So R equivalent will be the resistance, the sum of all the resistors, each individual. All right. The wall of the house has 3 layers, so you have some wood, and then you have some insulation, and then you have some plasterboard, some like sheetrock or older material plasterboard. On a cold winter day, the outside, let's put the outside over here. Let's put a temperature. The outside is, it doesn't really matter which side I put it on. It's just that I should have the plasterboard or the gypsum, GYPSUM, gypsum on the inside of the house, and the cold on the outside where I have the wood siding. That's -5 degrees C. Okay. All right. And a convection coefficient H on the outside of 60 watts per meter squared Kelvin. Okay. So this is my insulation. All right. And let me try and organize my thoughts on it. Temperature on the inside is 25 degrees C with the H on the inside of 20 watts per meter squared Kelvin. All right. The total area is given, so it's 180 meters squared for that area. And determine the total heat loss through the wall. So the heat is going to be going all the way through the system. Just kind of sketch it like that. Q. What's our heat loss? Well, just as we said, we need to get each of those resistors, magnitudes, sum them up, get the total. So it'll be the 1 over the H on the inside the area. Now this area is 180. You can leave it off, but probably for the beginner, put it in, and you're just going to be using that 180, 180, 180 because you're going to have the L over Ka. Hey, what's that value of A in that equation? 180. And then you're going to have L over Ka for the insulation. What's the area? 180. Okay, this is a simpler way to leave that area off in a while, but let's not do that. Let's just compute each one of these resistances, L over Ka for the wood, and then 1 over Ha for that. Okay, so I did this already, and you can kind of see the results. This is the resistance for the convection on the outside, and it's a really small number, isn't it? I should have even shown more digits in Excel. It has units of degree C per watt. Maybe for the wood, maybe the insulation is a little easier to reproduce. Let's see if we can reproduce this number by hand. Can you reproduce this number by hand? What would I do? I'd come in here, and that's this layer right here. What is the thickness L of my insulation from the information given? 0.045 meter. The thermal conductivity of my insulation, 0.04 watts per meter degree C. And then what is my area? 180 meters squared. Okay, that's the resistance of my insulation. Can you check my units? Will I get degree C per watt? Sure doesn't look like it, does it? But it does, doesn't it? The meters go, kind of funny. And that degree C comes upstairs. And there you go. Now, if you have a calculator, some people want to run it for me and give me a thumbs up or thumbs down. 1 thumbs up. Good. Were you able to reproduce it? 2 thumbs up. 3 thumbs up. Thank you very much. Anybody else? 4, 5. Perfect. Okay. So I had enough digits out here. Now in Excel, it kept all the digits in there, so it's just a display issue. Now what I did was I summed them all up, and there's the sum. So if I want to find the Q, isn't it my overall delta T? Now be careful because you're going from 25 to -5. So what's my delta T? 20 or 30? You're going from 25 to -5? It's not 20. That's a common error. It's 30. Thank you very much. You were all good. So you have 30 divided by the sum of the resistances right there. And it comes in at that many watts. And there's your answer. So 3,820 watts. Now there's a little diagnostic right over here. What do you think that is? 1%, 10%, 80%, you know. It's the fraction of the overall resistance due to each of those layers. So how do we get this 80%? Well, we took the resistance due to the insulation and divided by the sum of the resistances. And you find out, hey, that layer contributed 80% of the overall resistance. And then what about the convection on the outside? 1.2%. Which of these 5 terms is negligible? The mostly negligible, the smallest contribution. Wouldn't it be the convection on the outside? Isn't this one? If you're going to neglect one of these, you would neglect this one. Now in engineering, this is a lot different than sometimes in science and other areas. In engineering, engineers get really good at figuring out what they need to pay attention to and what they can ignore. Somebody says, well, I think we really need to study the convection on the outside of this wall because we need to get that. You know, it could be 58 watts per meter squared Kelvin. How do you know it's 60? It could be 61.3 watt, and that's going to affect the answer. Yes, it'll affect the answer, but as an engineer, it's going to affect it to what's dominant in this problem is the resistance of the insulation. You need to make sure you have a good estimate of the thickness of that insulation, the effective conductivity of that insulation, before you start arguing about the appropriate value of H. Because if you're in the ballpark with that value of H, you know, and everything else is appropriate, then essentially that H doesn't matter. You know, the difference between this value of 60 and 65 is not going to change your bottom line Q. Hopefully that makes sense. I'm trying to just instill a little insight into the problem. So if I was had a limited budget and I needed to really get a good answer for this problem, I would focus more attention where the majority of the resistance is. I would focus it on the insulation. All right, let's move forward. There's some more details. Let's move forward. Resistors can be in series. Resistors can be in parallel. What does a parallel look like? Well, remember you have maybe an electric resistor network, and then you could have gone this path to here or that path to there. And then maybe it goes back like this. Well, help me a little bit. These two are in parallel, aren't they? So if, let's say this was a value of R1 and this had a value of R2, could I somehow collapse those two resistors that are in parallel into an equivalent resistor? And then this would be maybe R3 and this is R4. What is the R equivalent? Do you remember the equation for R equivalent? You're a genius. No, you just had to solve so many problems in your education that you just know these things, right? Did you see this equation in physics? Multiple times. Did you see it in circuits? Multiple times. Did you see it in other classes, like this class? Yes. So don't leave home without it. So there you go. And then here you have this one. Now you have this equivalent resistor, and you can add it to R3 and you can add it to R4 just like we did for in series. And so thermal analysis builds on this type of thing. It's done quite often. So we have a wall. Anybody did little home construction? You know, I was gonna get out of high school and I went to work. I can drive by buildings. My wife's like, don't tell me I know you helped construct that apartment complex when you were about 18 years old. You know, driving around town like, yeah, I worked on that job as a carpenter. I did. Anybody else a carpenter? Build stuff? Well, there you go. You should all, you know. So what's a wall look like of a home or a building? Anyway, what they have is typically some long wall. You'll have some outer sheeting and some inside material, and you'll have some material they call studs. Often in a home, it's 2x4 studs, right? And those studs are on a center, the center distance. And they don't like to change it. They like to have it nicely spaced, and often they're on 16-inch centers for studs. Okay, the 2x4 studs. And if you're up north, they won't have 2x4. They'll have 2x6 studs for thicker walls, more insulation, and that's not common down here at all. And they'll even have steel studs instead of wood studs. And but anyway, so if you wanted to analyze the flow of heat through the wall of a house, forget the windows, forget the doors, just look at the wall. This is easy now. And it's the same thing for the ceiling. The ceiling has those rafters going across, okay, and they're frequently spaced at 16 inches or a little wider. Most of it's 16 inch. Okay. So what you would do is you can get a section of it and analyze the section. Here, what have they shown you? I tried to grab this out of the textbook. They kind of cut and cut right there. That means this is a symmetry section. I flip it and I flip it and I keep flipping it and I build out my wall conceptually. So you could cut and do this in the middle of the stud to the middle of the stud and analyze that section. Or you could analyze the section where you're going from the middle of the insulation to the middle of the insulation. And that's what they've done here. They've got like that. Middle of the insulation and middle of the insulation. And one stud in the middle. And then you have to make some modeling assumptions. And you say, well, it's probably all of this surface right here is at a temperature, let's say T1. So I'm going to introduce a temperature, T1, that represents the temperature of the wood siding, the outside of the wood siding layer. And then I'm going to introduce another temperature, which is T2, which represents the wood siding temperature, but the other part of it, the other edge of it, the inside surface of the wood siding. Do you see that? I mean, I'm trying to make this clear without belaboring the point too much. And then what about this down here? We're going to introduce T3. What is that? Well, it's my wallboard temperature, but it's the inside, interior temperature inside the wall. And then T4 will be the wallboard temperature to the room. Let's say this is my room and this was my outside. So temperature of the wood siding on the outside, the temperature wood siding in the interior of the wall, the temperature of the wallboard on the inside, and then the temperature of the wallboard in the surface in the room. And then you could also have convection. You would say the temperature of the inside air, and you could have a temperature of the outside air. And you would have a resistor here of 1 over HA, the outside convection coefficient, and a resistor here 1 over the HN area. All right. But what do we have going on? This is a continuous slab for the wallboard, so that's easy. And then this is the slab for the siding. But what do we have here? Oh, we could go through the insulation or we could go through the stud. And the thermal conductivity of the insulation is a lot different than the stud, so I have two paths. So that's why we have two resistors to model thermally the heat transfer through this wall. One would be the path through the insulation, and one would be the path through the wood stud. Okay? Or metal stud if you had metal, whatever the stud is, whatever the supporting structure is. Okay. So here is an example where you have, I'm just saying it again, they're in parallel. Okay. A little bit of geometry to help you figure it out. Let's do the resistance of the insulation. Well, it's going to be the thickness of the insulation, the thermal conductivity of the insulation, and then some area for the flow. So in this problem, 130 millimeters. Is that 130 millimeters either L, K, or A? I'm trying to get this L over Ka for the insulation. What is the 130 millimeters? It's my L, isn't it? It's the length traveled. So this one is 130 millimeters, 130 millimeters. You go and look up the thermal conductivity insulate, 0.04 watts per meter degree C, or, I'm just throwing out a number. It's close in that vicinity. The hard part, that area. You can do it for a section, or you can do it for the whole wall. At this point, you look at the problem and all the information given, and you make a choice. Am I going to do it for a section or for the whole wall? If you do it for the section, you need to know this distance here, right? Right? And so if I said this is for the insulation, let's say this is, I don't know, let's pick 500 millimeters. This area is going to be 500 millimeters minus the 40 millimeters. What? Why am I subtracting 40 millimeters? Because it's not going through this one. You know what I mean? It's not going through the stud. I'm just doing the insulation. And then I need to multiply it by some dimension that's not shown, that's perpendicular to the screen, that's going down. Right? And so another choice. Am I going to pick 1 millimeter sort of third dimension, or 1 meter third dimension? That's a choice. So if you're going to maybe do a section, you have 500 millimeter length there, and then do down into the paper, into the screen, 1 meter, fine, that would work. So I would rewrite this as being 1 meter times 0.5 minus 0.4 meter. That way I have the area in meters squared. Did I lose anybody? But this is where you're going to lose points on exams or homework. You're going to get tripped up. You're not going to get the length right. You're not going to get the area. Come on. L over Ka. Pretty easy. We've taken heat transfer and boiled it down. It's pretty easy. But on the FE exam, are they going to give you credit if you can't get the right answer? Nope. You will fail. That's the FE exam. So we just got to do the bookkeeping right. Professor, I didn't sign up for accounting. I'm not a business major. But it's the same type of thing in accounting, the same type of thing in engineering. We just got to keep track of all the terms and not mess up on the numbers. All right, let's say I do it for the whole wall. Well, then what you need to do is you need to say, hey, for the whole wall, what is my length? And then I'm going to try and show it this way. What is my height for the whole wall? Wouldn't that give me the whole area? So if I was going to say, what's the area for the insulation? I would say, give me the whole area for the wall, and then subtract off the area for the studs. Okay? So let's say in the whole wall, it was, I don't know, the length here was, 20 foot, and it was not 3 foot, let's do more like 12 foot tall or something like that. So, 30 foot by 12 foot. How many studs are you going to have in there? Well, if you have one every 16 inches, that's you can do the math. I didn't do the math. I'm just making up the numbers. So what's that? 20 1.5. Let's say 14 studs. Let's say you had 14 studs in there, right? Well, then you would say, I got to subtract off the 14 studs times however wide the stud is, and then they're the same length. So the width of the stud and then the same height of the stud. So this would be the length and then the height of the wall. I'm trying to show you two approaches. How many people have already solved this homework problem? They realize I'm talking about a homework problem in Chapter 3. Some people, eager beavers, jumped into Chapter 3 already, started solving some homework problems. That's what I'm talking about, okay? I'm telling you how to help do the homework problem in Chapter 3, as well as one of the problems on the FE exam, high probability. It'll be something like this. Can you work it out? So sometimes it's better to work in a section. Sometimes it's better to work for a whole wall. Okay? Take your pick and then stay with it. All right. So once you get the right number of studs, you get that right area, you get the insulation area, then you get the number of studs, etc. And then you get numbers for these and then combine them. This one was for a wall of a certain height and a certain width with a certain number of studs. And you had siding, studs, insulation, the inside wall material, and you've got to get, I think, helpful to get the R's for the whole wall. And then you can sum them up, right? Notice that I took these two and I combined them. What did I do that for? Because I just can't sum when they're in parallel. I have to do the equation to get them to be the equivalent. So this is my equivalent for the insulation and the studs, where here I just copied over and then did the sum. Then I did a little analysis, and what's providing the insulation? Essentially the insulation in the wall. That's 94% of the resistance. That's a little extra insight into the problem. And then you can continue on and solve this problem. Okay? Hopefully this helps you set it up. All right. All right. Now we move to another topic. It's called contact resistance. It may not be that big of a deal in home construction, but it's definitely a big deal in electronics, cooling. And you have layers of things, and you're really trying to have small delta T's, not having your computer or your cell phone internal components overheat. Anyway, so you have material A in contact with material B, and there's this interface. If you blow it up with a magnifying glass, the rough surfaces, nothing's perfectly smooth, in contact with another rough surface. So it's like mountains pushing against, flipped over mountains. And so there'll be points of contact, but then there'll be what they call this gaps right in here. Well, what's filling those gaps is very important to the heat transfer, because as you have a temperature flow, the heat transfer steady state, it's as if there's a big temperature drop right across the gap due to this resistance because of the contact. So if it's filled with air, air has a low thermal conductivity. If it's filled with some sort of grease, like a liquid, then that's a much higher thermal conductivity, and it's higher. Maybe you put in there some metallic material that's very soft and compliant, and when you pressure, to push the two together, then it's going to have good thermal conductivity, filling most of the interfacial gap voids. So it really depends. I mean, you could try to get some sort of metal or metallic-based grease in there to promote the heat transfer to minimize this delta T. But anyway, the same type of equation. We say, hey, the flow of heat going across through, it's going through A, it's going through B, it's got to go through that gap, got to go through that interface, and is equal to something that's driving it. Now we're going to talk about a temperature difference that drives it just across the gap, just across that interface. And then you say, well, there's probably some thermal contact resistance. Make sense? All right, that equation makes good sense to me. Somebody says, I'd like to put it in terms of Q double prime. Hey, I forgot. What is Q double prime? Is that Q divided by A, or is that Q times A?
It's Q divided by A.
It's divided by A. That's our heat flux. All right, so units of watts per meter squared. Somebody says, I like this equation. I'd like to modify that equation to get Q double prime. No problem. I need to come over here and I need to put A RTC delta T. Does that equation make sense to you? Yes, it makes sense to me as well. But I'm going to tell you there's a little anomaly. I'm not the author of the textbook. The author of the textbook equation writes it like this. Q double prime, let me write a better Q on that. Q double prime is equal to delta T. What is that delta T again? Just the gap or the interface delta T divided by R thermal contact. I love everything up until this point. No. Because if this is the relationship between Q and Q double prime, what should be the relationship between RTC and RTC double prime? What do you think you should do? Should you multiply by area or divide by area? You should divide by the area, but this is the equation that the book uses, which is confusing. Sorry. But I think the book is consistent with a lot of the literature as well. But I know that a lot of the literature will simply put, they'll put it like this. 1 over TC is 1 over H contact. They'll just forget the R and they'll just put 1 over H contact. So it's like a convective contact resistance, but that's okay. This is not in the book. This is in the book. And you have to use what's in the book. Okay? So, this is our equation. Can you kind of tell what are the units, SI units of this R double prime thermal contact? Well, it's degrees C per, what is the units of Q double prime? I forgot. Watts. So it's meter squared. So it's meter squared degrees C per watt. That's the unit on this contact resistance. And again, I prefer contact conductance. Maybe you'll see that, but it's not in the book. What's in the book? That's what I'm trying to describe. So here's a table. And they give you, let's kind of read it. It's table 3.1, thermal contact resistance 4, and then they have metallic interfaces under vacuum condition or aluminum interface with 10 micron surface roughness and 10 to the 5th Newton per meter squared with different interfacial fluids. So I think we can understand A. A is vacuum condition. That's all of this. But what did they do here? They introduced a contact pressure. So this is a little confusing. This is a contact pressure and this is a contact pressure. Which is a higher contact pressure? That means I'm pushing the two materials together with a pretty good force, right? Pretty good contact pressure. And so if I take two stainless steels and I'll have a range of this resistance and a range of this resistance, does it go up or down? Does it make sense that you have a lower resistance at a higher contact pressure? Yeah, it's like smashing those little mountains down. And if you have something that's a little more pliable, then you have less, lower contact. And this copper is good too. All right, a couple points to point out here. This 10 to the 4, what does that mean? So if somebody says, I want you to get the value for copper under vacuum conditions at this interfacial pressure, and you're going to say, oh, it's between 1 and 10. Let's pick the value 5. Oh, does that mean RTC double prime is equal to 5 or 5 times 10 to the plus 4, or 5 times 10 to the minus 4, all having units of meter squared Kelvin per watt. The units aren't the issue, it's this magnitude. So let's just do a clicker, A, B, or C. You're looking at it, you're an engineer, you're about ready to graduate. You see this all the time in headers of tables. What is it? Should I use in my calculations 5 or 5 times 10 to the plus 4 or 5 times 10 to the minus 4? Well, this was a harder question, so we do have a spectrum of answers, right?
Wait. Can I change it now?
Nope, it's already in. All right, the majority is, or if that even is a majority, yeah, 67% is correct, but it is very confusing at times. And so you have to pay particular attention. What they did was they said, I took my value of R, and then I multiplied by 10 to the plus 4, and I took that number and put it in the table. So when I want to get back R, I take the number out of the table, and I have to divide by 10 to the plus 4, or multiply by 10 to the minus 4, to get the number that I need to use in calculations. I've explained that a number of times when I teach thermo. I explain it here. You really got to struggle with it on your own, and be careful. How many engineers can make mistakes by not doing that correctly? Just be careful. All right, so this is the correct one. So these are small numbers. Okay, now the other thing that I noticed was, man, they're very confusing. Look at this. They have this description of, but there's missing a kilo in front of that Newton. So I have a question for you. My last clicker question for today. Which statement is true? Because I'm confused. They have 100 kilonewtons per meter squared. They have 10 to the 5th newtons per meter squared. So is A, B, or C correct? Is one greater than the other, equal to, or less than? And again, the majority of the class is correct. They are the same. Don't ask me why then the author of the text decided to write 10 to the 5th here instead of just writing 100 kilonewton. I don't know why they did that, but they did it, okay? So anyway, leave that alone. All right, now let's take a look. There's a lot of information in the tables. Please spend some time looking at tables. If you change and you have this interspatial fluid of air, but now notice for part B, they're only doing the aluminum with the 10 micron surface roughness at that pressure. But they're changing for that aluminum, this is all the aluminum, they're changing from air, helium, hydrogen, silicon, glycerin. All right? So look at, helium has a high conductivity and air has a low conductivity. This is really bad, right? Well, the vacuum's even worse, isn't it? Look at the vacuum. It's poor. A lot of times they have thermal greases. Anybody did electronics work where you mount the heat sink? You have a little paste. You don't want to put too much, but you want to have a smooth layer and then have a good contact on it. There you go. All right, do I have time to solve this problem? We have 10 minutes. Should we talk about this problem or skip it?
We should definitely talk about it, yeah.
All right. We have heat dissipating electric components embedded in an integrated circuit, the chip that's very thin. So this is my very thin chip. Now they've given it some dimension in here just for to visualize it, but it's very thin. And in that chip, there's a Q double prime, meaning per area of the chip, there's some heat source. You know, electronics are dissipating some heat. Okay. They have some fluid, some coolant. It's some dielectric liquid at the top, and it has a pretty good convection coefficient, 900 watts per meter squared Kelvin, and a temperature, I got the wrong symbol, there's your H naught, and a temperature of 20 degrees C. It's joined to the circuit board by this board on the bottom, but it has a thermal contact resistance between the chip and the board. Aha, there's our little new piece of information there. Here's the value of it. Looks reasonable, 10 to the minus 4 meters squared Kelvin per watt. The board has a thickness, L sub B, of 5 millimeter, right here. And a thermal conductivity, K sub B, of 2.5 watts per meter Kelvin. The bottom surface of the board is also exposed to some fluid, but this time it's not exposed to a liquid, it's exposed to air. So it has a lot lower H of 40 watts per meter squared Kelvin versus, what was this up here? 900. And it has the same temperature. What did I do? I put that in the wrong place again. Of 20 degrees C. The chip heat dissipation is a whopping 35,000 watts per meter squared. 35,000 watts per meter squared. If that is what needs to be dissipated because electronics are running on the chip, what is that chip temperature? Find Tc. Well, you're going to find that it's about 52 degrees C, but how do you do it? How do you do it? Well, don't forget that energy is conserved. If you're dumping in that many watts, they have to go somewhere. So you can think about it being dumped in, and it has to flow either to the top or the bottom. So this is the temperature of the chip I'm trying to find. It's going to go out to a resistor, a convective 1 over H A resistor, to the temperature of the fluid at the top. That's out the top, which is 20 degrees C. And if it goes out the bottom, the first thing it has to get through is a resistor for the contact, that contact resistance. All right, let's just put resistance thermal contact. Okay, then it goes through a L over Ka slab through the board. Then finally, it goes through a 1 over H on the bottom, let's say HI area, convection, and then it's finally out to T infinity on the bottom, which is 20 degrees C. So you could calculate this temperature right there, not needed, the temperature right below the thermal interface, or the single chip temperature, that's what's really needed, right there. Okay? So what's being dumped in? You're dumping in Q double prime. Now, this is another place where you either do everything per 1 meter squared area or not. A lot of times just pick. Pick area is equal to 1 meter squared. So then this is, now I'm dumping in 35,000 watts, right? That's how much is coming in. Now, you could get 30,000 up that way, 5,000 that way. You could get 15, or whatever it is, 15, 20, some split. It's going to split, it's based on our resistances. All right, you can get this value of resistance. I put in my H of 900, and I put in my area of 1, voila. Okay, my thermal contact. I've got to get, look at our units on that, meter squared. Go back to it. Our contact, where is it? Meter squared degrees C per watt, right? So this was our funny, here, this is what I want. Sorry about that. So it's my R double prime TC, and I divide by 1 meter squared. It doesn't, because my area of 1 meter squared, it doesn't change the magnitude. It's almost as if I could have just ignored that double prime. Anyway, this comes in at 10 to the minus 4. And then this is the degrees C or Kelvin per watt. Just like this will be some number Kelvin per watt. Those are the units on my resistance. L over Ka, I have to get that. Remember the A is 1 meter squared. Same here, 1 meter squared. I have these three. Are they in series? Yes. Add them up. And then I look at it. This one goes to 20. That one goes to 20. It's as if both of them are 20 to 20 degrees C, the unknown temperature. These are in parallel. Voila. You can combine. You get one equivalent resistance for the whole network. A little harder if this is a different temperature than that one, but it's still doable. Okay? And then you calculate TC. TC comes in at 52. All right, I have a couple minutes. Let me do this. When you analyze this problem, sometimes it's better to sneak up slowly on a problem. Somebody says, you know what? Let's pretend that 100% of the heat from the chip has to go out the top. Nothing goes out the bottom. All right, if you did that, what you could find is that you could find the estimate of the chip temperature. It'll be a little higher than 52, but how much higher? If most of the heat's going out the top anyway, look at this is a very high convection coefficient, isn't it? That's a very high convection coefficient. This is a lot of resistance to get out to the bottom, and a low convection coefficient on the bottom anyway. So if somebody said, you know, just neglect all this complication down here and give me an estimate of the chip temperature, I'd say let's take it only out the top. And it would be a little higher, and our equation would be something like this. Let me clean it up. We'd have that the Q is equal to the, I'm going to abandon the H and A, like that, times temperature chip minus temperature of the fluid at the top. So you're going to have the temperature chip is equal to the temperature fluid at the top plus Q double prime divided by H. You can do this with your calculator right now. It's 20 degrees C plus, we had 35,000 divided by 900. What do you get? .9 degrees C. So because of the path through the bottom, it's going to be a little colder. It'll be down to 52. So I thank you very much for your attention. We'll see you next time.